quantum mechanics is really all about solving the Schrodinger equation. That's a bit of an oversimplification though, because if there was only one Schrodinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrodinger equation isn't just the Schrodinger equation, there are many Schrodinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrodinger equation. They're all slightly different, and they all require slightly different solution techniques. And the reason there are many different Schrodinger equations is that the situation under which you want to solve the Schrodinger equation enters the Schrodinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrodinger equation? This is the time-dependent Schrodinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This v of x is the potential energy as a function of position. As if this were a purely classical system. For instance, if the particle was found at a particular position, what would be its potential energy? That's what this function v of x encodes. Now we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see how this is related. This is the time-dependent Schrodinger equation, which is a little bit unnecessarily complicated. Most of the time we work with the time-independent Schrodinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e, which is just a number. This came from the separation of variables. It's just a constant, and we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrodinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position and you have psi, the wave function. So this v of x psi of x, if that varies as a function of position, and it will, if the wave function has a large value, a large magnitude in a certain region, and the potential has a large value in a certain region, that means that there is some significant probability the particle will be found in a region with high potential energy. That will tend to make the potential energy of the state higher. Now, if psi is 0 in some region where the potential energy is high, that means the particle will never be found in a region where the potential energy is high. That means the state likely has a lower potential energy. This is all a very sort of heuristic qualitative argument, and we can only really do better once we know what these solutions are and what these actual potential functions look like. What I'd like to do here before we move on is to rearrange this a little bit to show you what effect the potential energy related to the energy and how it's related to the energy of the state, what effect that has on the wave function. And in order to do that, I'm going to multiply through by this h bar squared over 2m and rearrange terms a little bit. What you get when you do that is the second derivative of psi with respect to x. There's my eraser. With respect to x being equal to 2m over h bar squared times v of x minus e psi. So this quantity here relates the second derivative of psi to psi itself. For instance, if the potential is larger than the energy of the state, you'll get one overall sign relating the second derivative in psi, whereas if energy is larger than potential, then you'll end up with a negative quantity here relating the second derivatives of psi with itself. So keep this in the back of your mind, and let's talk about some example potential functions. This is what we're going to be doing, or this is what the textbook does in all of Chapter 2. Write different potential functions and solve the Schrodinger equation. The first example potential we do, and this is section 2.2, is what I like to call the particle in a box. The textbook calls it an infinite square well. The particle in a hard box, for instance, you can think of as a potential function that looks like this. Get myself some coordinate systems here. You have a potential function v of x, oops, turn off my ruler, that looks something like this. This is v of x as a function of x. The potential goes to infinity for x larger than some size. Let's call this, minus a to a. If you're inside minus a to a, you have 0 potential energy. If you're outside of a, you have infinite potential energy. It's a very simple potential function. It's a little bit non-physical though, because, well, infinite potential energy, what does that really mean? It means it would require infinite energy to force the particle beyond a. If you had some infinitely dense material that just would not tolerate the electron ever being found inside that material, and you made a box out of that material, this is the sort of potential function you would get. Much more realistically, we have the harmonic oscillator potential. The harmonic oscillator potential is the same as what you would get in classical physics. It's a parabola. This is something, proportional to x squared. V of x being proportional to x squared is what I mean. This is what you would get if you had a particle attached to a spring connected to the origin. If you move the particle to the right, you stretch the spring. Put quantum mechanically, if you happen to find the particle at a large displacement from the origin, the spring would be stretched quite a large amount and would have a large amount of potential energy associated with it. From a more physical, down-to-earth sort of perspective, this is what happens when you have any sort of equilibrium position for a particle to be in. The particle is sitting here near the origin where there is a flat potential, but any displacement from the origin makes the potential tend to increase in either direction. This is like an electron in a particle trap, or an atom in a particle trap. Harmonic oscillator potentials show up all over the place, and we'll spend a good amount of time talking about them. The next potential that we consider is the delta function potential. And what that looks like, now I'm going to start at 0 and draw it going negative, but it's effectively an infinitely sharp, infinitely deep version of this particle in a box potential. Instead of going to infinity outside of your realm, it's at 0, and instead of being at 0 inside your realm, it goes to minus infinity there. This now continues downwards. It doesn't bottom out here. The overall behavior will be different now because the particle is no longer disallowed from being outside of the domain. There is no longer an infinite potential energy here. And we'll talk about that as well. These are all sort of weird, non-physical potentials. The particle in a soft box potential is a little bit more physical. If I have my coordinate system here, the particle in a soft box potential looks something like this. To keep things simple, it still changes instantaneously at, say, minus a and a, but the potential energy is no longer infinity. This is, for instance, a box made out of a material that has some pores in it, and the electron, or whatever particle you're considering to be in the box, doesn't like being in those pores. So there's some energy you have to add in order to push the particle in. Once it's in, it doesn't really matter where it is. You've sort of made that energy investment to push the particle into the box. And we'll talk about the quantum mechanical states that are allowed by this potential as well. Finally, we will consider what happens when there's no potential at all. Essentially, your potential function is constant. That actually has some interesting implications for the form of the solutions of the Schrodinger equation. And we'll talk about that in more detail. To map this onto textbook sections, this is section 2.2. The harmonic oscillator is section 2.3. the delta function potential is section 2.5. The particle in a box is section 2.6. Particle in a soft box is 2.6. And particle with no potential or an overall constant potential everywhere in space is section 2.4. So these are some example potentials that we'll be talking about in this chapter. What do these potentials actually mean, though? How do they influence the Schrodinger equation and its solutions? Well, the way I wrote the Schrodinger equation a few slides ago, second derivative of psi with respect to x is equal to 2m over h bar squared, just a constant, times v of x minus e psi. This is now the time-independent Schrodinger equation, so we're just talking about functions of position here. And E, keep in mind, is the energy of the state. If we're going to have a solution to the time-independent Schrodinger equation, this E exists, and it's just a number. So what does that actually mean? Let's think about it this way. We have a left-hand side determined by the right-hand side of this equation. And the left-hand side is just the second derivative with respect to position of the wave function. This is related to the curvature of the wave function. I could actually write this as a total derivative, since this is just psi is only a function of position now. So there's no magic going on with this partial derivatives. It's going to behave same as the ordinary derivative that you're used to from calculus class. The second derivative is related to the concavity of a function, whether something's concave up or concave down. So let's think about what this means. If you have a potential v of x that's greater than your energy, if v of x is greater than e, what does that mean? That means v of x minus e is a positive quantity. That means the right-hand side here will have whatever sign psi has. And I'm being a little sloppy since psi here is in general a complex function. But if we consider it to just be, say, positive, which isn't as meaningful for a complex number as it is for a real number, you would have psi of x. If psi of x is positive and this number is positive, then the second derivative is positive. Which means that if if psi is, say, here, psi is positive, when it's multiplied by is positive, then the second derivative is positive. It curves like this. Whereas if psi is down here, psi is negative, this is positive, second derivative of psi is negative. It curves like this. What this means is that psi curves away from our axis, away from this psi equals 0 line. On the other hand, if v of x is less than the energy, this quantity will be negative, and we get the opposite behavior. If psi is up here, positive, it's multiplied by a negative number, and the second derivative is negative, you get something that curves downwards. If psi is on the other side of the axis, it curves upwards. Psi curves toward the axis. So this helps us understand a little bit about the shape of the wave function. For instance, let me do an example here in a little bit more detail. Suppose I have, I'll do it over here, coordinate system. If I have a potential function, let's do the sort of soft particle in a box. I can do better than that. Soft particle in a box. So v of x is constant outside your central region and constant inside your central region and has a step change at the boundaries of your region. Let's think about what our wave function might look like under these circumstances. So we have our boundaries of our region here. The other thing that we need to know to figure out what the wave function might look like is a hypothetical energy. And I'm just going to set an energy here. I'm going to do the interesting case. Let's say this is the energy. And I'm plotting energy on the same axis as the potential, which is fine. This is the energy of the state. This is the potential energy as a function of position, so they have the same units. What this energy hypothetically means is that outside here, the potential energy is greater than the energy of the state, and inside here, the potential energy is less than the energy of the state. So we'll get different signed sort of behaviors, different curvatures of the wave function. So, do my wave function in blue here. If I say, start my wave function, this is all hypothetical now, this may not work. If I start my wave function here, at some point on the positive side of the axis, at the origin, we know the energy of the state is larger than the energy of, or than the potential energy. So this quantity is negative, and psi curves towards the axis. So since psi is positive here, I'm looking at this sort of curvature. So I could draw my wave function out sort of like this. Maybe that's reasonable, maybe that's not. This is obviously not a quantitative calculation. This is just sort of the sort of curvature that you would expect. Now, I only continued these curving lines out to the boundaries, since at the boundaries, things change. Outside our central region here, the potential energy is larger than the energy of the state, and you get curvature away from the axis. What might that look like? Well, something curving away from the axis. It's going to look sort of like that. But where do I start it? Do I start it going like that? Do I start it going like that? What does this actually look like? Well, if you think about this, we can say a little bit more about what happens to our wave function when it passes a boundary like this. And the key fact is that if v of x is finite, then while we might have the second derivative of psi with respect to x being discontinuous, maybe, might not be. In this case, the second derivative of psi is just set by this difference. So when we have a discontinuity in the potential, we have a discontinuity in the second derivative. The first derivative of psi will be continuous. Think about integrating a function that looks like this. I integrate it once, I get something maybe with large positive slope going to slightly smaller positive slope. There will be no discontinuity in the first derivative. What this means for psi is that it's effectively smooth. And that by that I just sort of mean no corners. The first derivative of psi won't ever show a corner like this. It will be something like that, for example. No sharp corners to it. What that means in the context of a boundary like this is that if I have psi going downwards at some angle here, I have to keep that angle as I cross the boundary. Now once I'm on the other side of the boundary here, I have to curve. And I have to curve according to the rules that we had here. So depending on what I actually chose for my initial point here and what the actual value of the energy was and what the actual value of the potential is outside in this region, I may get differing degrees of curvature. I may get something that happens like this, curves up very rapidly, or I may get something that doesn't curve very rapidly at all. Perhaps it's curving upwards very slowly, but it crosses the axis. Now, as it crosses the axis, the sign on psi here changes. The curvature is also determined by psi. As psi gets smaller and smaller, the curvature gets smaller and smaller, the curvature becoming 0 as psi crosses the axis. Then when psi becomes negative, the sign of the curvature changes, so this would start curving the other direction, curving downwards. It turns out that there is actually a state right in the middle, sort of a happy medium state, where psi curves, and just kisses the axis. Comes towards the axis, and when it comes towards the axis and reaches the axis with 0 slope and 0 curvature, it's stuck. It will never leave the axis again. And these are the sorts of states that you might actually associate with probability distributions. You know, if psi is blowing up like this, going to positive infinity or to negative infinity, that your wave function will not be normalizable. But the wave function here, denoted by these green curves, has finite area, therefore is sort of normalizable. So these are the sorts of things that the potential function tells you about the wave function. In general, what direction it curves, how much it curves, and how quickly. And of course, doing this quantitatively requires a good deal of mathematics. But I wanted to introduce the math, or before I introduce the math, I wanted to give you some conceptual framework with which to understand what exactly this potential means. If the potential is larger than the energy, you expect things that curve upwards. And when you get things that curve upwards, you'll have, or curve away from the axis, you tend to have things blow up unless they just sort of go down and kiss the axis like this. So there will be a lot of things approaching the axis and never leaving, so that we have normalizable wave functions. On the other hand, if the potential energy is less than the energy of the state, you get things that curve towards. And well, if you have something that curves towards, it tends to do this. Always curving towards, always curving towards, always curving towards the axis. You get these sort of wave-like states. So that's a very hand-waving discussion of the sorts of behavior you get from, in this case, step discontinuous potential. And we'll see the sort of behavior throughout this chapter. To check your understanding, take this step discontinuous potential and tell me which of these hypothetical wave functions is consistent with the Schrodinger equation. Now, I did not actually go through and solve the Schrodinger equation here to make sure these things are quantitatively accurate. They're probably all not quantitatively accurate. What I'm asking you to do here is identify the sort of qualitative behavior of these systems. Is the curvature right? And let's see. Yeah, are the boundary conditions right? In particular, does the wave function behave as you would expect as it passes from the sort of interior region to the exterior region? Enters the Schrodinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrodinger equation? This is the time-dependent Schrodinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared. Quantum mechanics is really all about solving the Schrodinger equation. That's a bit of an oversimplification, though, because if there was only one Schrodinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrodinger equation isn't just the Schrodinger equation. There are many Schrodinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrodinger equation. They're all slightly different, and they all require slightly different solution techniques. And the reason there are many different Schrodinger equations is that the situation under which you want to solve the Schrodinger equation, E, which is just a number. This came from the separation of variables. It's just a constant. And we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrodinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position and you have psi, the wave function. So this v of x, how this is related. This is the time-dependent Schrodinger equation, which is a little bit unnecessarily complicated. Most of the time, we work with the time-independent Schrodinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This v of x is the potential energy as a function of position. As if this were a purely classical system. For instance, if the particle was found at a particular position, what would be its potential energy? That's what this function v of x encodes. Now we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see